All right, everybody, let's talk about some work. This is going to be fun. Look, slightly different format. Instead of me writing, we're going to try this out. Check out, oh, look at that. Energy is the ability to do work. So what is work? Work is done whenever a force is applied over a distance. In other words, work is energy, and energy is the ability to do work. Not the best definition, but that's the world in which we live. You are welcome. Here's an equation. It says work, W, is equal to a force times a distance, FD. It's not exactly what the equation is, but it'll suffice for us. One important factor in here is, though, that F and D must be in the same direction. So what does this mean? This means that if a force is at some angle, you have to figure out, using trig, fun stuff, how much of that force is in the same direction as the displacement. And we'll get to examples of that soon. All right, but that is an important fact. So you will have to do trig to figure out the component of the force that is in the same direction as the displacement. But in general, we can think about work as a force times the distance. All right, so the bigger the force, all right, the more work that you do. The bigger the distance, and I really should say displacement, the bigger the displacement, the more work that you do. It is also important to note that work is a scalar quantity. Energy, in fact, is a scalar quantity. So we're taking the vector force, we're taking the vector displacement, we're multiplying them together, sort of, and then we're ending up with this scalar quantity that is work. Work is a scalar, see? And it's measured in joules. Joules is our unit of energy. It's a big old capital J, and it's named for Mr. Joules. You are welcome for all that work. Here it is again. Force times a distance, or force times a displacement. A force is a mass times an acceleration, so work makes you mad. Duh, there you go. You can remember that, right, boys and girls? All right, 1 joule, okay, is equal to a Newton, which is the unit for force, times a meter. I'm not sure. It looks like this got screwed up just a little bit. But anyway, so there's kind of a fudgy little example of what this is supposed to be. Obviously, this isn't correct, so this got messed up just a little bit. I'll try to fix it in what we in the business call post. I don't know if that'll happen or not. Okay. Unless the mass moves, no work is done. Meaning that you could be pushing something really hard. You can be getting all tired and stuff and do no work. Since it's a force times a displacement, it means also that if the thing ends up back where it started, no work is done. So again, you go to the gym, you're doing tons of work. Do work, right? You're getting all swole. All right, and then you put the weights right back on the rack, right where you got them from. You've done no work the entire time. You've wasted your life. Just kidding. You got to do that. Got to keep it fit, yo. All right, so here are some fun examples. Maybe I'll cut to me being super awkward, all right, here. But again, you're leaning on that wall, you're pushing on that wall. No work is done, no displacement. Okay, there I am in all my glory, leaning against that wall. Excellent. Okay, look, holding a box in the air. How much work is done? None, because there is no displacement. No displacement. Don't be alarmed by the lack of all capital letters either. You are welcome for that. Little fun. Also, this art is not my best. Oh, what about lifting that block, which is 10 newtons? Again, 10 newtons is the weight. I could give you the mass. If I gave you the mass, you need to use that mad part of the equation. All right, and you need to figure out what the force you would need to apply. So the force you need to apply to hold something up is the object's weight. So I'm just holding it there. I'm lifting it up into the air, rather. I'm bending just at the waist for some reason, not even bending my knees. This is not something I can do. And then you lift it up. So you take that block, you bend at the waist, and you pick up a blue box, apparently, and then you lift it up into the air. 8 joules of work is done. I applied the force in the direction of that motion. I lifted the box up into the air, all right, and then, applied a force over a distance. I applied a force over a displacement. Perfect. Excellent. Ooh, interesting one here. We are carrying the box. Okay, so the displacement of this box is from left to right. Well, what is the direction of the force? Well, if I'm holding this up into the air and I'm running at a constant speed, or carrying it, whatever, the direction of the force is vertically. That means that the force that I'm applying is perpendicular to the displacement, which means what? No work is done. They're perpendicular to each other. What? You are crazy. All right, so this is just the thing, okay? It is not the work that we know of in the vernacular, which means you're getting tired, you're doing something, you're getting paid. All right, it is just you are in the specific case of the force and the displacement. How much of that force is causing that displacement? None of this force in this last example here is causing that displacement of 5 meters. None of it. All right, they're perpendicular. All right. I'm not going to dwell on this too much. This gets into that same sort of thing. Okay, so what is the force and the direction here? We'll talk about this in other terms and other ways, because we can talk about this in a couple of different ways, right? We can talk about the force being applied directly up the ramp. We can specifically talk about the force done against gravity. So there's a few different examples here. Moving along. Energy is a scalar quantity. Boom. It comes in many forms. All right. Specifically here, we are talking about mechanical, and we're going to be talking really only about mechanical. But here are some other examples: electrical, chemical, nuclear, sound, whatever. All right. Thermal we'll touch on too, but thermal is really kind of lumped into mechanical. And I think I have a mistake in a minute that, I'll use words, and then sometime later somebody will be like, you said it wrong, and I'll be like, shut up, and they'll be like, sorry, and I'll be like, me too. All right. It is measured in by the amount of work it can do. All right. So however much work you can do is however much energy you have. It's this really weird definition of and how we understand energy and work and how they're related to one another. But something we gotta hang with. All right. And then just a brief aside. Power is the rate at which work is done. We're not going to focus on this too much, but here it is. If you do a bunch of work and you do it really quickly, high power. You do a bunch of work, right, and you do it really slowly, low power. And again, like the denominators here are all screwed up. Thanks a lot, Google. All right, and whatever. It's supposed to be power is equal to work over time, all right, which is equal to a force times the displacement over time, which is also equal to a force times a velocity. So this is screwed up. That's annoying, but I'm not re-recording this, so you're going to have to deal with it. We'll see it again. All right, power is measured in joules per second, also known as watts. All right, and there's a couple other versions of how we can rewrite that in more fundamental units like kilogram meters squared per seconds cubed. That's fun. All right, but joules per second or watts is a reasonable way to think about power. It's the rate at which you're expending energy, how much energy you're using. It's a weird way to think about it, but maybe a normal way to think about it. I don't know. I don't know what's weird and what's normal. And that's it. Okay, so that's a general overview about what work is. We'll take another crack at energy and stuff. We'll start talking about potential and kinetic and all that fun stuff. So hopefully this was as fun for you as it was for me. You're welcome. Have a great day. Just kidding. See you tomorrow. Wait, that's not right.